Good morning again, TCA, Trinity Classical Academy. It is I again, Justin Bourgeois, your instructor. I wanted to first do some pointing out. There might be a typo in your lesson plans. Your guided practice, or not your guided practice, your practice 10.3 begins on page 276. So whatever I have in the lesson plans, it's at the end of this lesson, 276. And I may have made a mistake with blue jelly beans or red jelly beans getting the numbers switched around. That misspeaking has also been pointing out to me. I didn't go back and listen because it doesn't matter. Hopefully you know what I mean. But turn to page 266 with me. We're looking at the approximating probability using real data. So in the real world, I hate when people say that, real world. In practice, let me say it that way. In practical settings, there are researchers who will gather data, and I gathered a little bit of data that I want to share with you guys. And they use that data to calculate probabilities, and it's usually pretty doggone close. So like they'll do surveys, or they'll take measurements, or use population data or sample data. There's a lot of different ways to gather and interpret and process data, which is just the information that we can observe and measure. And so this lesson is going to really just barely scratch the surface of those kinds of concepts, and give you kind of an initial exposure to some of those concepts and things. Looking at it, so we're going to find the relative frequency in a relative frequency. Relative means compared to something else, right? So relative frequency is how often does this happen compared to the other things. So like an event like drawing a blue jelly bean out of a jar has a relative frequency. So if you're not sure how many blue or red or yellow jelly beans are in a particular container, you could just take a sample, pick random ones out, and then say, okay, I'm pretty sure there's a lot more blue ones in this jar or whatever. So here I'm going to read in that blue section on page 266. In a chance process, you keep repeating an action and keep track of the outcomes. Although you know all the possible types of outcome beforehand, you do not know what the next outcome is. The outcomes you have collected are called data or observations. So the vocab, you see that yellow box vocab, there's relative frequency, there's observed frequency, that's the data that you have observed. Experimental probability, so that's the probability of an experiment, and then there's theoretical probability. Let's look at the hands-on activity, the HOA, not the homeowners association, but the hands-on activity. It has you flip a coin 20 times and record heads or tails, and then count the number of heads, count the number of tails, and your total should add up to 20, assuming that you followed the instructions. I felt like that was lame. I'm sitting here in my warehouse of sorts, and I've got this bucket of dice that I've had sitting there. So I actually did my own experiment. But just a second. So looking at this, you see the observed frequency is you flip the coin 20 times, you're expecting to get about 10 heads and about 10 tails. In practice, though, assuming you're flipping the coin fairly and you have a fair coin, that might there's still a really reasonable chance that you might get more heads than tails, more tails than heads. How many times have you flipped a coin and got heads 3 times in a row? Like that's not very probable to happen, but I mean it does happen sometimes. As often as we flip coins, it's going to happen to where you'll get the same result multiple times in a row. So I grabbed a die out of my I'm going to shake it so you can. I have a bucket of dice. It's like a fishbowl shaped thing. It's full of weird dice that have symbols on them, numbers on them, words in different languages. There's like a Korean dice. I don't know. There's a lot of really weird stuff. There's a die that says scalene, isosceles, equilateral. It's got different types of triangles on it. I don't know what that's for. There's apparently a gender reveal die that says it's a boy or it's a girl, or and it's dice. I don't know. It's weird. But I grabbed some 4-sided dice. In nerd speak, we call this a D4. First I did a blue one, and here are the results that I got. I rolled it 20 times. I got a 2, then a 1, then a 2, then a 1, then a 2, then a 3, then a 2, then a 2, then a 2, then a 3, then a 2, then a 4. Woo, first 4. Then a 3, then a 2, then a 3, then a 4, then a 2, then a 3, then a 2, then a 3. I started to suspect that maybe this die was not balanced. And when I rolled this thing, I was throwing it up in the air, spinning it. It was bouncing and clattering all over this table until it stopped on a value, and 2 came up half the time. Like, that is so beyond what I would have expected. Because theoretically, the theoretical probability should be 25%, right? A fourth of the time it lands on 2, because there are only 4 outcomes. There's a 1, there's a 2, there's a 3, and there's a 4. So I suspected that maybe the blue die was a little bit weighted. These are my cheap dice. My bucket of premium dice is somewhere else. And so I had my cheap dice with me, and I suspect these cheap dice are poorly made, that the weight tends to tip one direction, and that direction tends to favor the result of a 2. So then I pulled a black one out, also a cheap one, but I got these results: 3, 1, 4, 3, 2, 4, 4, 2, 4, 1, 3, 1, 2, 3, 4, 1, 3, 4, 2, 1. Black, at first glance, appears to be a more fair die. It appears to have results, observed outcomes, and observed frequencies that would more closely resemble what we should expect from a very fair and purely random die. Looking on page 267, just say step 2. So we've got the raw data. It says, what's the observed frequency? Let's use that blue die. It says, what's the observed frequency? And so using the observed frequency, I hate when it does this. For the blue die, we have the result of a 1, result of a 2, result of a 3, result of a 4. So we have, I already counted, there were 10 times the number came up as a 2. Let's count the ones. I don't think there are very many. I think there are 2. 1 came up twice, and early on. See, this is why you can't. It takes multiple iterations, multiple experiments to really get a good feel for how a die is rolling. Because at first I got a 2, a 1, a 2, and a 1. After those 4 rolls, I'm like, gosh, I wonder if I'm ever going to get anything higher than a 2, and especially the 5th. So 2, 1, 2, 1, 2. It looks like this die strongly favors 1 and 2, but then I didn't roll another 1 for the entire rest of the experiment. So out of 20 trials, I only got 2 results of a 1. Let's count the 3s. 1, 2, 3, 4, 5, 6 3s. So out of 20, I would expect about 5 of any given number. So 3 is a little bit, is very close to what I would expect. And then 4, it took me forever to get up to a 4. So I was, let's see, 5, 6, 7, 8, 9, 10, 11, 12. I was 12 rolls in before a 4 showed up, and there were still only 2. So looking at the relative frequency, first of all, let's make sure this adds up to 20. So to calculate the relative frequency, you take the observation divided by the total. And the total number of trials was 20. And so for the relative frequency, if we're going to calculate this, and I know this isn't hands-on, you're just watching me do it, but the relative frequency, go ahead and follow along and try it yourself with something. I don't know, just test your dice, see if your dice seem fair. In reality, gosh, I wish I could remember this study. Some statisticians who use probabilities and study math, they figure out what is a statistically significant number of dice rolls to determine if a die is fair, and it's something in the hundreds. Like, you have to roll that die a lot to really test it, and so there's just no way to feasibly test all the dice that are out in the game stores to see, is this truly a fair die or whatever. Maybe Las Vegas has a very strong interest in making sure their dice are completely unbiased, or their roulette tables or things like that. Like Las Vegas, they spend a lot of resources checking on their stuff. So obviously half of, so the observed frequency would be 0.5 here. I'm just trying to keep my digits straight. So 6 over 20 would be 0.3. And 0.1. So all of these observed frequencies, so here we go, 1/10, 5/10, 3/10, and 1/10, they should all add up to 1.0. That should always be true all the time, forever. Because, and look at enthusiastic math student at the bottom of the page in example 10, she says, because each relative frequency represents a fraction of the total number of people, the sum of the relative frequencies is 1. Check it. So this is one of those times where you always should check. On this kind of a problem, check. Does it add up to 1? Otherwise, let's take a look at what I did wrong. And there we go. So back in the hands-on activity, so the relative frequency, you can write it either as a fraction or a decimal. And step 4 says, what's the sum of the relative frequencies? It's 1. So judging by this blue die, I would say at first glance, and it's not statistically significant, I would need to calculate my my chi-square value and do some advanced statistical analysis to figure out what's my degrees of freedom that I need for this kind of a statistical modeling to determine is a 4-sided die biased or not. But at first glance, I would say seems to be a compelling case. I would argue that this looks biased. It looks like it's biased in favor of 2, which if I'm playing a game and I want to roll higher than a 2, then I'm going to be sad if I use this blue little tetrahedral die. Okay, that was a little more time than I wanted to spend on that, but hopefully you're on fast forward. So let's look at example 10, y'all. Example 10, so the table shows the relative frequencies of men, women, and children at a park on a particular day. On that day, 600 people were in the park. I would be curious, how do they gather this data? Did they gather it continuously throughout the day, since the park was opened until the park closed? Or was this a snapshot in time where they said, okay, I'm going to record right now. What's the relative frequency? So 54% of the people in this park are men, 37% are women, and 9% are children. Is that what they're doing? I don't know, but it's curious. We're turning the page. We're on page 268. So it says how many children were at the park. Well, it says there were 600 people at the park. Okay, sorry, I missed that detail. So it says on that day 600 people were in the park. So if 9% of them were at the park, 9% or 0.09 times 600 gives you the answer of 54 children at the park. Must be a big park. I'm assuming it's not your neighborhood playground. How many more men than women were at the park? You'd have to calculate the number of men, calculate the number of women, and then find the difference, and you determine 102 men were at the park. Sorry, I'm just kind of flying through this, but you guys can read example 10 yourself. Read the example 10 yourself, because it's going to help you to do guided practice number 1. Pause the video. Haha. Guided practice number 1. Here we go. I'm actually going to move over here. So we're on guided practice number 1. Page 268. Guided practice 1. So the first one, A, it says how many 17-inch monitors were sold during the sale. We have to multiply. Why? There we go. We have to multiply the relative frequency. So 30 out of every 100 were 17-inch monitors. How many 17-inch monitors were there? Well, 30% times 640 equals 192. There were 192. Oops. Let's not do that. Let's do this. That is how we do it. So 0.3, you can use calculators, times 640 equals the number of monitors, 192. Number B, how many fewer 14-inch monitors were sold than 15-inch monitors? So we have to calculate how many 14-inch monitors there were. So there were 0.15 times 640. These are the 96, and then we subtract, so then the other one would be so 55% of the 640 equals 352. We subtract that, we get 256. There were 256 fewer 14-inch monitors than 15-inch monitors. So, Galaxy Pen, come back. There we go. There's your answers. Moving on. Haha. All right. Has anybody ever watched Speed Racer? Haha. He was a Japanese cartoon. He would just go, haha. I'm going really fast. Haha. You cannot catch me. Haha. And I don't know. I just did a haha, and it reminded me of how ridiculous Speed Racer was. Haha. Okay. Page 269. Find the relative frequency from a frequency histogram. Histogram. No, histogram. All right, the histogram shows the frequencies for the data grouped into intervals. You can also use a relative frequency histogram to display the data. Example 11. At some schools, a grade point average, a GPA, is used to describe academic progress. The histogram shows data about the GPAs of 400 students at a school. I think TCA will do this beginning in rhetoric school, but don't quote me on that. It could change. So the break, so look at that blue math note. The break squiggly thing is in the horizontal axis means that there is a break in the scale from 0 to 2. So what they're saying is they could draw the scale like this, or draw the chart like this, and then have, 1, and then 2, and then 3, and then start the graph over here. But they're like, no, we're not doing that. Forget all this. We want the relevant data to be close to the origin, and so we're going to do this little squiggle jiggle right here. That shows it's called a break. I just drew it without the break again. Squiggle jiggle. So instead of starting with 1, they're going to start with 2. But I mean, this could be 100, depending on what you're graphing. You could say, hey, it doesn't get relevant until we get all the way up to 100, and then we go like, aha, 110. What's with me today on aha? I don't get it. Am I like it? Oh, I must be the evil twin. Today I must be the evil twin. That explains why I'm acting so evil and trying to take over the world. I must hurry up and finish my math video so that I can continue my global conquest. All of my ambitions. Okay, that was the math note. Anyway, moving on. Histogram is a vertical bar graph with no spaces between the bars. Each bar represents an interval of the same size. The lower value of each interval on the histogram shows the least possible value for the interval. The upper value shows the least possible value for the next interval. You get that? So the interval means it's not a range. So like you could do a histogram with like solid numbers, like a 2 or a 3, or you can say it's between 2 and 3, or between 2 and 2.5, like they do here. So your grade point average might be 2.110. Your grade point average might be 3.145. Your grade point average can have lots of decimal numbers in it, and that's why they're using intervals. So it's a range from, there are 128 students, between 2 and 2.5. So if your GPA is 2.0, aha, there you are, you're in that interval. If yours is 2.5, then which interval are you in? Are you in the 128 students, or are you in the 160 students? Well, let's read. The upper value shows the least possible value for the next interval. So for example, the bar for the interval 2 to 2.5 shows the frequency for GPAs in the range. Your GPA is greater than or equal to 2, but is less than 2.5. So the interval, this bar, starts here and goes up to there. The next interval starts on exactly 2.5. So if you have a GPA of exactly 2.5, you are counted in this bar, not in the one on the left. If your GPA is exactly 2.5, you're counted in that bar. All right, that's how a histogram works. An interval histogram anyways. So example 11 says, what's the relative frequency of students whose GPA is at least 3? So greater than or equal to 3. Give your answer as a fraction. As a fraction. Okay, so how many students do we have? We're looking at the chart. We got 80 of those and 32 of these. It goes all the way up to 4. You can't go higher than 4. Straight A's means you're 4.0. Hey, hang on a second. Well, that's okay. The reason why it's okay is because there's no other interval over here. So otherwise, generally that rightmost digit would show you the next interval, but because there is no next interval, we know that these 32 students can go up to and including the 4.0. Roger that. 10-4, good buddy. All right, so we gotta addition these all together. So 400 students. We don't need to use addition. The information on the top of the page says 400 students, and also we could look at that and say, yeah, that looks like 400 students. 128 plus 160 plus 80 plus 32. Glad to see no one's doing less than a 2.0 GPA. All right, so what is the relative frequency of students with a GPA of at least 3? Guys, let's look at this. So at least 3 means everyone from here to here. This whole chunk is what we're after. So all of those students. So what's 80 plus 32? We got to find that out. So that's 112. 112 over 400. Out of 400 students, they told us to give the answer as a fraction. Ordinarily, I would prefer either a decimal or a percentage. Percentages are just nice. I like percentages. So this simplifies down to 7 over 25. Because you should be able to see, hopefully, that 112 divides by 4, but then you can divide more because that's not enough. I don't know. Simplifying is something that we are not going to review. Oh, let's see, caution. Oh yeah, I already did that one. Okay, turning the page, haha. We're on page 270. Maybe I'm going crazy. If you heard that song, they're going to take me away, haha. They're going to take me away, ho ho, to the funny farm, where life is beautiful all the time. B, find the relative frequency of students whose GPA is greater than or equal to 3 but less than 3.5. Okay, so now they just want this chunk. It's the same thing that we just did, but instead of including this, we're gonna not include that, and we're just gonna include this. So now we're doing it with 80. 80 out of 400 equals, now they want it as a percent. Oh, now they're changing it up, those crazy guys. So 80 over 400 equals 20%. It's 1/5. 20%. Then it says draw a relative frequency histogram using percentages. So basically it's going to look exactly the same, except we're going to, instead of writing numbers, we're going to write percentages. So letter C, draw a relative frequency histogram using the percentages. So it's 1B 32%, and then 40%. Yep. So neat and pretty, 20%. And then 8%. You know what? This school must be really strict with their grading. I'm just going to say, to have 40% of the students between 2.5 and 3, having more than half of the students doing less than a 3 GPA, tells me I would question their grading practices. There might be some grade inflation going on there. Right? All right. Let's not criticize fictional schools anymore. Instead, let's do zippity bippity 271. We're going to do guided practice numero dos. This one looks like a doozy. Don't spend all day on it. I mean, just kind of work it. I want you to work it, and I want you to be doing good at it. I want to say pause, but hang on just a second. So, excuse me. If you get good at doing this kind of problem and you practice it enough that you start to get fast with it, that'll help you to do the checkpoint for this kind of problem. Like you will not be, so I don't, it would be very tempting to look outside and see how pretty it is and say, I'm gonna just fly through this really quick. I'll watch Mr. Bourgeois solve it for me. But putting pencil on paper and doing the work is going to make your checkpoint go much better. So now, having said that, pause the video and actually do it. Word to your mother. Righty-ho. So, gotta practice, copy and complete and solve. I don't really necessarily expect you to fill in all those blanks, but it's good to just kind of do the work. So, Alexis and Joe caught 40 fish over the weekend. Crikey. The histogram shows the masses of the fish they caught. On the histogram, the interval 14 to 16 includes data for fish that have a mass of at least 14, but less than 16. So first, what does that mean? And is that relevant for how we solve this? It could be. It can be, depending on if they're asking for frequencies, and we need to know, does that include the line? So the 14 to 16, that's the farthest right bar. I'm just gonna not worry about that squiggle. It almost looks like I tried to draw a squiggle right there, but I didn't. So we got 8, and then over here we got 16, and so it looks like this. They caught 5. What do you call it? What's that fishing term? A lunker? A lugger? I don't know. Some kind of a doozy of a fish. There's like a fisherman term. If I was a fisherman, I would know the fisherman term probably. Or if I had fisherman friends, I would understand the fishermen and how they do. So it looks something like that. That's a crude representation, but hey, you should draw neater than that since you have paper and not a screen. The relative frequency of the fish that have a mass of at least 8 but less than 10. So that is exclusively this bar. And look at what I did. I didn't even draw my histogram correctly. So anyway, so that's 6. 6 out of the 40 fish that they caught. So for A, what does it say? Give your answer as a percent. The answer is 15% for A. How do we do that? Well, we take 6 divided by 40. There are 6 fish that have a mass at least 8 kilograms, but less than 10 kilograms. Kilograms. Think Alexis and Joe are European, perhaps? Could be. They might be Canadian. They're probably Canadian. A. That's why they went fishing. That's all I have to do there. All right. So out of every 40 fish they caught, there were 6. Guys, right here, you can just, I know they have all the extra steps for you, but they say give your answer as a percent. So really all you have to do is take 6 on your calculator, divided by 40, and it should give you 0.15. And we know that is 15%. And that's your answer. Number B, draw a relative frequency histogram using a percent. So basically what we're going to do, like we did in the last one, it's the same, everything is the same, all the bars are the same size compared to each other. We just have to calculate each number and take it divided by 40. So 6, so this was a 6. 6 divided by 40 was 15, we already did that one. 17 divided by 40 is going to be 42.5%. And then 12 divided by 40 will equal, and does truly equal, 30% or 0.3. And then that other 0.5% we see over here. Das Vidanya, darling. There it is. That's Russian. I think it means goodbye. Das Vidanya. All right, guys, moving on through. Whistling? Probably not. What? Zombie lines showed up on my whiteboard. Scary. All right, what I meant to do was this. Boop, 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 boop. What is going on? I do not understand. All right. Guys, we are on page 272. Use a relative frequency as a probability. So if Alexis and Joe caught those fish, we could say that we can kind of make an assumption. So it says that from the guided practice, since 42% of their fish were between 10 and 12 kilograms, we could say, the odds are you're probably going to catch a fish that is less than 12 kilograms because more than half of their fish were less than 12 kilograms, but at least 8 kilograms, depending on, I don't know, a lot of factors, the bait they used. Relative frequency is based, so now I'm reading out loud. Relative frequency is based on observations of what has happened in a chance process. It is also used as a probability measure to predict the likelihood of a future outcome. For instance, suppose you toss a number die, that means a 6-sided die, not one weird like mine that was 4-sided dies, tetrahedral, 100 times. You'll find that the relative probability of rolling a 5 is 0.18. So you rolled the die 100 times, you got the number 5 18 of those times. You say that the experimental probability of rolling a die, of rolling a value of a 5, is 0.18. An experimental probability is a probability based on the data collected or observations made in an experiment. The type of probability you learned about earlier is called theoretical probability. A theoretical probability is the ratio of the number of favorable outcomes to the total number of possible outcomes. You do not have to perform an experiment to find a theoretical probability. For instance, suppose you roll a number die, you know that the theoretical probability of rolling a 5, let's figure it out, rolling a 5, so getting a value of a 5, how many different outcomes are there? There's 1. 5 is 1 out of 6 possible values on that die. So on your calculator, take 1 divided by 6 and you'll see, 0.1 with a 6 repeating is the odds, or should be the odds, of rolling a 5 or a 2 or a 1 on a fair 6-sided die. However, when you did it 100 times, you got a couple more 5s. You got 18 instead of 16 and a 7th, or no, 6 instead of almost 17. Now, anytime you roll a 100-sided die, you can't, 100 times anyways, you can't perfectly get 0.166666666. You can't roll 16 and a fraction times, right? So some number is going to occur more than others if you roll a die 100 times. That's just how it's going to happen, because 100 doesn't divide evenly by 6. So there. All right, continue reading. Observing the types of vehicles passing an intersection. So let's suppose we're sitting and watching an intersection. Maybe that's your job. I've seen people with that job. The types of vehicles passing through an intersection were observed one morning. The observed frequencies and relative frequencies are summarized below. Car was observed 108 times. So the relative frequency is 108 over 160. I'm not doing the simplified numbers because that confuses me. It should confuse you too. It should. Simplifying the fraction makes it hard to compare across the rows. Motorcycle was observed 12 times. Van was observed 16 times, and truck was observed 24 times. They're assuming that that's, well, I mean, nothing else was observed. That doesn't fall into one of those categories. Like there was no one riding a camel through the intersection, so we're not even going to list those. In this experiment, 160 vehicles were observed. Among the 5 types of vehicles observed, cars had the greatest frequency, 27 over 40. You may also write this as a decimal or a percent, which is what normal people do. So 67.5%. You may use the relative frequencies in the table as the experimental probabilities to predict what is likely to occur. For example, you could say, well, it seems like there's a 67.5% chance that the next vehicle passing through will be a car. You see how that works? You're using observed data to make assumptions, pretty reasonable assumptions, about what is likely to occur next. This is kind of how practitioners operate in finance, in science, in statistical analysis, even in like social sciences, political sciences. They'll say it is 80%, it was 80% likely for Hillary Clinton to win. That does not mean that she is guaranteed to win the election. As we even if you say it is 80%, I predict an 80% chance of Hillary Clinton winning. I mean, there's an 80% chance that I will roll higher than a 2 on a 10-sided die, but sometimes I will roll a 1 or a 2, which means Donald Trump can win the election. I mean, theoretically, we all know that's not actually going to happen. Okay, so that was a joke. I know a lot of you did not laugh, but that's okay. I still love you. Let's move over to page 273, example 12. So use the relative frequency as an experimental probability to make a prediction. So you spin the spinner shown in that little picture. It's got, I assume those are colors, but it's got A, B, C, D, and E. And record the letter that the pointer lands on. We don't know, guys. We don't know if this is a fair spinner. In fact, spinners are really, really, really hard to make fair because any kind of little like grain of sand or dust can make it slow down in one spot on that spinner. Well, that was a lot of sibilance in that sentence that I spoke. Sibilants are the S noises that people make when they speak. FYI. All right, moving on. So here are the observations: A, B, C, D, E, 36, 44, 28, 52, and 40. Ooh, look at that. So so this is 200 spins. Find the relative frequency for each of the letters, then write the frequency as a decimal. So they just do it. You just calculate 36 over 200, 0.18, 44 over 200, 0.22, 28 over 200, 0.14, etc., etc., etc. So let's see what enthusiastic math student has to say. The letter E has a relative frequency of 0.20, which means that the spinner landed on the letter E about 1/5 of the time. Does that make sense? I think so. So B, if you spin the spinner again, which letter would you predict the spinner is most likely to land on? After 200 times, oh, see, here's something that a lot of people will say. They'll say, oh, I'm due. Do you guys remember, perhaps some of you remember the Super Bowl? There's so many people look at the Super Bowl and all this stuff, and oh my goodness. So for the first, what are we on, Super Bowl 50? 50 something, I don't know. For like the first 50 Super Bowls, every single one was heads. The coin flip was heads. It came up heads every single Super Bowl. What are the odds that it's going to be heads again? Think about this. I'm going to look it up. While you think about this, I'm going to look it up. I think it's still recording. Yeah, I'm still recording. Okay, good. All right. Super Bowl coin flips. How are we doing, Super Bowl coin flips? All right. I don't know. Maybe I'm wrong. I'm looking it up, and I think I'm second guessing myself. Oh no. Okay. Well, this is completely wrong. It came up heads, tails, heads, tails, heads, tails. There's a lot of variation. Well, what was it? There was some statistic that I let's see. Maybe it was, so Super Bowl 54 was the recent one. Tails, tails, heads, tails, tails, tails. Heads, heads, heads. Tails, tails, tails. I don't know. There was some statistic that was like an unbelievable number. Maybe it was the Pro Bowl. I don't know. I'll look it up later. There was some statistic where a coin toss came up heads so many times in a row that people were like, they're due for a tails, but it's still a 50-50 chance. It could be heads, it could be tails. It's a 50-50 chance. So you can't say, oh, I'm due for something, because that's not the way probability works. But anyway, looking at that spinner, I would say that spinner tends to favor the letter D. So if we extrapolate the data and draw a conclusion that says the spinner is 26% likely to land on the letter D, that's the best way to do your figuring. So we're still on example 12, but it bleeds over into page 274. So what is the likelihood of not getting a letter D? What are two different ways that we could solve this? So if 20, let's just say that the spinner likes the letter D more than all the other letters, right? So this spinner likes the D. We'll go ahead and murder this. That's all right. So the spinner likes the letter D. So if 26% of the time we get D, how do we figure out what are the odds of not getting D? Well, I think the easiest way is to do this. 100% minus 26%, right? We'll get 74%. So if there's 26% of it is D, Venn diagram. So 26% of it is D. The complement of D, D prime, as I like to call it, is the remainder. So we have 26%, and then this is 74%, right? A bar model could also help if you like those. The other thing you can do is add up all the other slices. So all the other slices add up to 74%, but let's not make this any harder than it needs to be. So guys, pause the video, do guided practice number 3, and then we will have one last little snippet of reading to do, and then we'll be done. So I'm due. That saying means, oh, if I haven't rolled a 2 in forever, that means that 2's got to come up now, right? It doesn't work that way. I like to say it because I think it's hilarious. Like, oh, this particular individual has never been able to hold a job for their whole life, which means they're due for a success. I better hire him. No, don't. It's a trap. I got to practice. Lucas made a dartboard shown in the diagram below, or on the right. He threw a dart at the dartboard 100 times. He recorded the number of times the dart landed on each color. The number of times he missed the dartboard was also recorded. So red, yellow, blue, and miss. Find the relative frequencies. Here they are. I'm just going to go down the list and read them. Landing on red. So red is 1/10, or as a decimal, it's 0.1. Yellow is 7/20ths, which is 0.35. Blue is 12/25ths. If you simplified it, I mean, it says to express it as a decimal. So as long as you get the decimal, that's fine. 0.48, and then the misses are 7 out of 100, which is 0.07. Lucas, don't miss, at least not very often. So B, explain what the relative frequency of the dart landing in the red region means. So it means that the event of landing in the red region has a relative frequency of 0.1, or 10%, which means that the dart landed in the red region about 10% of the time. C, if Lucas throws the dart again, predict which region it's most likely to land in. The correct answer is that you should predict it will land in the blue region because that has the greatest relative frequency of 0.48. So that's what I got for you. Okay. Now we're on page 275. We got this little blue snippet. I'm not going to do that. You're welcome to do the hands-on activity. I will not try and stop you. Actually, I might try and stop Brianna from doing that. I might. I think I will. Brianna, you better not do that hands-on activity. I'm gonna stop you. Compare the long-run relative frequency and theoretical probability. There's actually a really cool video about this on Khan Academy, where he explains, oops, sorry, I'm trying to speak and type at the same time. Good night. I think it's called long-run probability. What is the matter? Probability. Come on, fingers. I like Khan Academy. If you guys don't like him, you have no taste. He's great. The lecturer is wonderful. but he has an experiment running where it has little balls dropping into a spot, and you see that if I flip a coin 20 times, I might get a lot more heads than tails, but if I keep flipping it and I get up to like thousands of times, it's going to be really, really close to being 0.5 as the heads and 0.5 as the tails. And that's what this little paragraph is talking about. Most of the time, experimental probability differs from the theoretical probability, but if you continue to carry out that experiment long term, you'll find that it starts to get closer and closer and closer to that theoretical probability. So like when they rolled that die 200 times and we said the 5 came up as 0.8 relative frequency, if you only roll a die 6 times or 60 times, you might get a lot more 5s. The relative frequency might be something like 0.25. It might be something really high, but it will start to get close to that 0.16 repeating that you get in the theoretical probability. So that's just kind of a something for you to know, that if something truly is a fair random outcome, it will, in the long run, even out. That's what I told. So my mother-in-law played. We taught her how to play Risk. You roll a lot of dice, and she said, "This is just all randomness. It's just all a bunch of random chance." And I'm like, "Well, but there's like hundreds of dice rolls in this game, so it really smooths out to where the randomness of it doesn't influence the game too terribly much, because it really depends on strategy. Because I am terrible at that game, and I tend to lose. So anyway, hope this was not as horrible as a sharp stick in the eye, and we'll see you soon-ish. Bye.